day to one and all. Today we're going to talk about solutions, the dissolution process, and electrolytes. Let's jump into it. So first of all, solutions, what are they? A solution is a homogeneous mixture of two or more substances. And there's two important definitions that we need to invoke here to understand them. There's the solute. A solute is a minor component in a solution, and the solvent, which is the major component in a solution. So we usually say that you dissolve the solute into the solvent. An aqueous solution, that's going to be particularly important in the rest of this class and in other chemistry classes, is a solution where water is the solvent. Pretty important solvent. So what are some examples of solutions? Well, they come in all sorts of different phases. So for example, we can have gas dissolved inside of a gas. An example would be air. So the air that we breathe in is about 78% nitrogen. We'll call that the solvent. About 21% oxygen, solute. And then we've got helium, neon, argon, CO2, methane, etc. Another example, a liquid solvent with a gas solute. An example of that would be a carbonated beverage, something with CO2 dissolved into it. We can dissolve solids into liquids. An example of that would be a sweetened beverage. If we want to get really crazy, we could dissolve both a gas and a solid into a liquid, and we could make soda, if you will, or pop. You can also make solutions with metals. So we can have a solid dissolved into a solid, and other solids as well. So for example, a metal alloy, something like brass, for example, is metal dissolved into another metal. So now science has afforded us an invaluable look into worlds previously thought to be invisible. Now, let's take a look at this ultra-realistic footage of what happens in the dissolution process of sodium chloride, NaCl, and water. So water has intermolecular forces that hold it together. There's our solvent. So these waters are attracted to each other. It's going to take some energy to break them apart. Okay, so we have to put in a little bit of energy to do that. Once we do, whoosh, okay, it's free. But now the solute that we're dissolving, the Na plus and the Cl minus, they have these ion-ion interactions. So they've got this electrostatic thing going. It's going to take energy to break them apart. But it can be done. Then swarm, our solvent. Now we can have these solute-solvent interactions that take place, and that's kind of the payoff step in a dissolution process. So now that we have these intermolecular forces that were just formed in this new solution, that's what I like to think of as the payoff step, which allows these things to actually go to fruition. So, as a quick click, what type of interactions did the solute and solvent enjoy at the end of that incredibly realistic movie? Take a moment, pause it. You did it! Ion dipole. So we had our ions, our Na plus and our Cl minus, and they were interacting with the dipoles of water, the partial positive hydrogen side and the partial negative oxygen side. So solutions are created because of these solute-solvent interactions. That's what allows the favorability of these interactions is what allows solutions to be formed. So, taking a more realistic look at what's happening here. So let's look at the dissolution of sodium chloride in water. Water forms what's called a solvation sphere around the Na plus and the Cl minus. We can see here that, so we have our Na pluses, and the Na pluses, the positive charge of sodium is attracted to the partial negative of water, and then our chlorides here are attracted to the partial positive side of water. So when water swarms around and dissolves our NaCl, that's when we get the dissolution and it forms the solvation sphere. Basically, I like to think of the water swarming around the solute that it dissolves. So let's look at the energies of the dissolution process. Breaking bonds and interactions, is that endothermic or exothermic? What's endothermic? It requires energy to break these stabilizing interactions. However, when you make bonds, you make new interactions, that releases energy. That's an exothermic process. So let's look at the energy changes involved during the dissolution process. We start off, our solute and our solvent are mingling with themselves. Well, first we need to be able to break apart the solvent. So our solvent, our solute, it doesn't matter which order we look at this in. First, here we're breaking the solute particles. So we have our solute and we're breaking it apart into their respective particles. We also need to do the same thing with our solvent. So both of these processes are endothermic. It takes energy to break apart our solute. It takes energy to break apart our solvent. Then, like I said before, comes the payoff stage. So then when the solute and the solvent form their interactions, then energy is released. So if we look at this, we had two endothermic processes and then one really exothermic process. The overall net change in this is the enthalpy of the solvation here, the dissolution process. So we call that delta H sub SOLN for solution. And here we can see that there's an overall net negative change. It's exothermic. It doesn't have to be though. This can be endothermic or exothermic. So if you add together the two endothermic processes and the magnitude of the exothermic process is greater, then the overall process will be exothermic. Many salts, when they dissolve, it is an exothermic process. But if you add together the two endothermic processes and the magnitude of the exothermic one isn't greater than that, then you're going to end up with an overall endothermic process. These ones are more driven by something called entropy, which has to do with randomness, disorder, something that you'll cover more in Chem 112. Okay. An example of this, of a endothermic dissolution process would be like a cold pack. So when you mix together the ingredients in a cold pack and you form the solution, it ends up actually taking heat from the environment and getting cold. So we have an overall endothermic process. So a big theme over the next 2 weeks is going to be solubility. And solubility is actually really important for understanding a lot of phenomenon around us. In fact, a lot of biochemistry and organic chemistry comes down to this idea of solubility. And solubility is the tendency for a solute to mingle, to dissolve into a solvent. So here are a few examples. We have heptane and cycloheptane. Heptane and cycloheptane only have London dispersion forces going for them. It turns out that molecules that form similar types of intermolecular forces have a better tendency to dissolve within each other. So heptane and cycloheptane, for example, would dissolve pretty well. We call this the like dissolves like principle. So lots and lots of hydrocarbon, like a massive amount of hydrocarbon character will dissolve readily in something else with a lot of hydrocarbon character, because that final step where you get the solute solvent interactions ends up being more favorable. So something like cyclohexane or heptane and water, however, they don't share their primary intermolecular force. Now, water still has LDFs, but water also primarily relies on dipole-dipole interactions and hydrogen bonding. So it turns out the energetics of trying to mix together heptane, cyclohexane, and water doesn't work so well. And you've probably seen this phenomenon if you've ever ordered salad dressing, oil and vinegar specifically, and allowed it to separate. You get the oil that ends up being on top and the vinegar, which is dissolved in water on the bottom. So in this case, if we were to try to pour together the two, the water is more dense, the water will go to the bottom, and the hydrocarbons will go on top. Now, ethanol is interesting because ethanol has a little bit of hydrocarbon character. So it's got, it's carbons and hydrogens in it. But it also has this polar character. It also has the ability to hydrogen bond in it as well. So ethanol is kind of a hybrid between the two. It can do all of these types of interactions. It mingles well with things that do LDFs. It mingles well with polar molecules and things that can contribute hydrogen bonding to that OH group, the alcohol. So ethanol turns out will actually dissolve in these hydrocarbons and in water here. So the ethanol will dissolve readily in both of these.
To illustrate this principle, I'm coming to you live from my kitchen. Well, not really, pre-recorded from my kitchen. So, what we're going to do to show this principle is, we have olive oil. We have the molecules in here. We have these triglycerides that consist largely of long hydrocarbon chains. And we have water in this cool, nifty beaker. So I'm going to pour the two of them together into this vessel. So I'll pour in the water, pour in the oil, that's long hydrocarbon chains, and do they seem to be interacting readily with each other? Well, no. They're forming these immiscible layers. And just to kind of make this a little bit cooler, so I have here a blue food dye. Next week we'll talk about the like dissolves like principle. But this particular blue food dye happens to have a lot of OHs in it. So it interacts readily with water, not so much with hydrocarbon chains. I'm going to put some in here. And notice that it's not really mingling. It's forming these droplets, not so much dissolving. Now there's some surface tension down here, the oil and water. Once we break that interface, promise this is going to look really, really cool. It's breaking. Once we break that interface, we're going to have it entering the water. Break. Break. Break the interface. And now that's in the water. Turns out that this dye is quite soluble in the water. So I'm going to give this a nice shake. It's dissolving readily in the water. And I might have shaken it too much. We'll come back to this. There it is.
So now let's take another look at that dissolution of NaCl, considering the energetics of it. So we have to break apart the Na plus and the Cl minus. That requires energy. That's an endothermic process. We also have to break apart the hydrogen bonds and the dipole-dipole interactions and the LDFs holding together water, chiefly the hydrogen bonding in there. So both of those require energy to go in, but then again, that payoff step is when the Na plus and the Cl minus can form those favorable ion-dipole interactions with water. So we have those ions interacting with the dipole. It releases enough energy to make this overall a favorable process. And salts and electrolytes are what we're going to spend the rest of today focusing on. So, salts, what do they do? Do they do things? Let's find out. The answer, yes. Yes, they do. And generally, we can classify salts into kind of two very broad categories. Metallic salts are a pretty classic example that we've looked at all throughout the semester, where you have a metal and a non-metal, or a collection of metals and non-metals together. So generically, we'll just call it MX, where we have some metal and then some non-metal X. Okay, ammonium salts are also pretty prevalent. Most common example is ammonium chloride, NH4Cl. So these are actually held together. Anytime you have a nitrogen with 4 bonds on it, it has a positive formal charge. It can form interactions with anions to create what's called an ammonium salt. So what we're going to be looking at today is what salts do in water. Any salt that's dissolved into water, that's solvated by the water, will dissociate into its ions. It will have the water molecules intercalate between the ions and split them apart. Enter the concept of electrolytes. And we can generally show this process through that generic reaction down there. Our salt MX will dissociate into M plus, the cation, in this case metal, and X minus, a non-metal, the anion. So electrolytes, what are they? They are substances that dissociate into ions in solution or facilitate the creation of ions in solution, allowing for the conduction of electricity. Why is it that they conduct electricity? Well, for the flow of electricity, you have to have the movement of charged particles. Ions carry said charge. So by having these ions in solution, if you have some sort of electric potential set up, you can usher these ions one way or the other, and you have electricity. So in class, we like to show this really cool demonstration where we actually use solutions to complete a circuit. Basically, the way it works is we have some sort of external source of electricity, AC current, and we plug in a light bulb that has a circuit that is broken up into the solution. Some solutions will be able to complete the circuit viably and allow electricity to move through and light up the bulb, some won't. So let's take, for example, a strong electrolyte like NaCl. So we can throw in NaCl into our water, and we can turn our water into salt water, because the Na plus and Cl minus will be broken apart. And then now that we have these ions, they can facilitate the movement of charge. So our circuit is complete, and our light bulb lights up. Really, really bright in this case. So now let's look at some data that we've taken from this experiment. What we have is a series of light bulbs. Some require more power to light up than others. So the 7.5 watt light bulb doesn't require that much power, but you still need to have a viable circuit in order to light it up. The 40 watt one, you're gonna need to have a pretty good circuit in order to do that with this experiment. So if we pour NaCl into water, it will light up all of these light bulbs. So the 7.5 watt bulb, check. 25 watt, check. 40 watt, check. So it is a strong electrolyte. It dissociates readily into ions to facilitate the movement of charge. Distilled water, not so much. Distilled water is a non-electrolyte. Now it turns out that 1 out of every 10 million waters or so actually auto-ionizes into H plus and OH minus, but pretty insignificant in the grand scheme of things. Tap water, on the other hand, it turns out can light up the 7.5 watt light bulb. State College water is harder than a brick. There's a lot of dissolved ions into it. So we're just going to chalk this up into the weak electrolyte category. There are some dissolved ions, some magnesium, some calcium, etc. Methanol. So methanol is a simple type of alcohol. Methanol is not going to get the job done. It's a non-electrolyte. It's not dissociating readily into ions. How about this next thing is acetic acid. 0.1 molar acetic acid will light up that light bulb. It does an okay job with the medium power light bulb and not so much on the 40 watt. So this is a weak electrolyte. We'll see the reaction that it undergoes, but it turns about 1 out of every 1,000 or so of acetic acids. It's the active ingredient in vinegar, gives it its punchy taste, will dissociate into ions. More on that in just a moment. NaOH. NaOH will light up that bulb, and that bulb. It is a strong electrolyte. It is a strong base. Again, well, we're going to take a closer look at a lot of these. Then we have ammonium chloride and ammonium salt. Salts are strong electrolytes. Wham, 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 strong. HCl. HCl is a classic example of a strong acid. What makes an acid strong? Again, stay tuned. But it'll dissociate readily into H plus and Cl minus. So it lights up that one, it lights up that one, it lights up that one, it is strong. Next we have a sugar, C12H22O11, a disaccharide. This one's a non-electrolyte, not going to break apart into ions. And then finally we have Gatorade. Gatorade, big selling point of it is refuel with electrolytes. I mean, they don't say it like that, but it's got electrolytes. It's got various salts in it. So again, what is required for the light bulb to light up? We need electrolytes, because those electrolytes are what facilitate the movement of charge. And so the solutions that do have these electrolytes in them have a better conductivity. They have a better ability to conduct electricity and complete the circuit. Okay, so now let's look at acids and bases. Acids and bases have a number of different useful definitions. For our purposes, we're going to focus on basically their calling cards in aqueous solutions. And what I mean by that is, if you put acids and bases into water, what do we notice an increase in the concentration of? Acids increase the hydronium ion concentration, H3O+. So a good example is hydrochloric acid, HCl. When it's put into water, it readily breaks apart into Cl minus, and the H plus will interact with the water and form this hydronium H3O+. Now it turns out hydronium is basically, I like to think of it like a pinball game where you have it bouncing around. So we have a hydrogen bouncing around between lots of different waters. So we can represent it like this, or we can represent it as just HCl dissociating into H plus and Cl minus. So this is a reasonable simplification. And generally speaking, when you do, later on in Chem 112, when you do calculations involving acids, you can treat acids as being a source of H plus or H3O plus. They're considered to be synonymous. Then we're going to look at an Arrhenius base. An Arrhenius base is anything that increases the concentration of hydroxide in an aqueous solution. So KOH is a classic example, potassium hydroxide. It first goes through the solvation process when we put it into water. So the water kind of swarms around it, and then it'll dissociate completely into its constituent ions, the K plus and the OH minus, the hydroxide. So acids, their calling card is H plus hydronium, and bases, their calling card is hydroxide, OH minus. It is very, 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 very important to know the classic 7 strong acids and what makes something a strong base. We'll have just a general rule we can use to figure out strong bases. There are more strong acids and strong bases in this. Some of them you might utilize in organic chemistry, but for our purposes, these are the 7 strong acids. They are hydrogen and a halogen, HCl, HBr, and the friendliest acid of them all, hydroiodidic, HI, high. Okay, so we have HCl, HBr, HI. These are all just a halogen and a hydrogen. You'll notice that there's a halogen not on there, more on that in just a moment. In the words of the great poet and philosopher John Bon Jovi, whoa, we're 3/7 of the way there. But there's more. There is sulfuric acid, H2SO4. There is nitric acid, HNO3. There's chlorous acid and perchloric acid, which look pretty similar. We have HClO3 and HClO4. These are our 7 strong acids. You'll notice HF is not a strong acid. Turns out that hydrogen-fluorine bond is too short. It's really strong. It doesn't get dissociated that readily in an aqueous solution. About 1 out of every 1,000 HFs will. We'll look at HF in just a moment. But those are the 7 strong acids that you want to be familiar with. For the strong bases, it'll help if we have a periodic table to consult when looking at these. Strong bases are any group 1 metal hydroxide and any group 2 metal hydroxide, excluding beryllium and magnesium hydroxide. So any group 2 metal hydroxide, calcium and below. So to the periodic table, da-da-da-da-da-da-da-da. So we have like lithium hydroxide, sodium hydroxide, potassium hydroxide, rubidium hydroxide, cesium hydroxide, etc. And then any group 2, calcium and below. So like for example, CaOH2, SrOH2. Each of these needs to be paired with 2 hydroxides because if we think about the charge on a group 2 metal, B plus 2. So in order to neutralize the charge, it would need 2 OH minuses there, okay? So et cetera, et cetera, et cetera. So some examples of these are lithium hydroxide, sodium hydroxide, potassium hydroxide, and then calcium hydroxide, strontium hydroxide, et cetera. That's how we can identify a strong base. So what makes an acid or a base strong? When it goes all out. So for all intents and purposes, 100% ionized in solution. So HCl, boom, turns completely into H plus and Cl minus. CaOH2, calcium hydroxide, boom, it turns completely into calcium 2 plus and 2 hydroxides. HF, is it a strong acid? No. So it goes through more of this kind of wishy-washy process called an equilibrium. And we talked a little bit about equilibriums when we discussed phase changes. But an equilibrium is when you have a forward process and a reverse process. So these reactions reach a point where their forward rate and their reverse rate is the same. And so we're not getting any net increase in the products. We're not getting any net increase in the reactants. We just have this sort of chemically ideal product-reactant ratio called an equilibrium. Strong acids and strong bases, on the other hand, basically 100% ionize. And I mentioned this before, but hydrofluoric acid, about 1 out of every 1,000 or so of the HFs will dissociate. So the product-to-reactant ratio is about 1 to 1,000. They're not dissociating that readily. Still enough to be an electrolyte, just not nearly to the extent as their strong acid, strong base counterparts. Here's something called electron pushing. And I think this is very useful for visualizing what's happening with some weak electrolytes, specifically with amines. So weak electrolytes, like HF, we can picture it breaking apart into H plus and F minus. But it turns out that ammonia, NH3, will readily create hydroxide, OH- in aqueous solution. How does it do that? So here's a skill called electron pushing, which we're not responsible for in general chemistry, but it's very, very, very useful in organic chemistry. And it actually turns out it tells us why reactions occur. It tells us actually how electrons flow to create new bonds and break old bonds. So in order to think about this, let's think about some principles that we know. On this water here, what is the partial charge on that hydrogen? Well, electrons are, pushed more toward the oxygen. So we have a partial positive. Do you see anything on that nitrogen that might be attracted to that partial positive charge? Well, the nitrogen, it's got a partial negative. It's got that lone pair of electrons. It's got a lot of electron density. Positives, negatives, they attract. So it's all like, ooh, a partial positive proton. And that's exactly what it says. So I like to think of electron pushing as almost like what happens with a crane game. So the electrons reach out and try to grab onto a proton. And much like the success rate of the crane game, about 1 out of every 1,000 or so will actually succeed. So anyway, the electrons reach out, and when they do, we end up forming a bond. So what we're seeing down here is that the lone pair of electrons actually forms a new covalent bond by grabbing onto the hydrogen. Hydrogen, though, can't take 4 electrons. It's too small. Can't be, 1s4. So something's got to give. So the covalent bond that was holding it to the water then breaks apart. And then voila, we're left with our products. We're left with our NH4+, our ammonium, and hydroxide OH-. So this is kind of a visual look at how weak bases work. Here's the actual reaction itself. So we have ammonia, NH3, reacting with water. Again, this is a weak electrolyte. So we're using that equilibrium arrow to show this is happening, but not to a major, major, major extent. So strong electrolytes, they dissociate completely to form ions in water. Our 3 classes of strong electrolytes are strong acids. For example, nitric acid, strong acid, dissociates completely into hydronium and nitrate. Strong bases. So for example, calcium hydroxide dissociates completely into calcium 2+ and 2 hydroxides. And then finally, ionic compounds and salts. And again, we have 2 types, generally speaking. We have a metal and non-metal. So here's an example I like to call chacuna, sodium acetate. It'll dissociate completely into acetate, CH3COO- and sodium Na+. And here we have it sort of color-coded. So the Na+ will break off from the CH3COO- in an aqueous solution. The water will intercalate it readily. We also have ammonium salts. And an ammonium is what you get when you have a nitrogen that has 4 bonds on it. It has a partial, not partial, it has a full-on positive formal charge, and it can form ionic interactions and ionic bonds with anions. So there we have ammonium. That's not complete. Oh, there's its partial, or not, I said partial again. There's its full-on positive formal charge. And look, there's chloride. Positive, negative, attraction, opposites attract. So this will dissociate completely in water. Water will easily be able to interrupt that interaction in an aqueous solution. So we have them turning into NH4+ and Cl-. Weak electrolytes. There are 2 classes of weak electrolytes that you want to recognize for Chem 110. You do want to know what weak electrolytes do. They dissociate partially. The strong ones dissociate completely. They're strong, they go all out. The weak ones, a little bit, okay? So we use the equilibrium arrow to show this process, to show it's not going completely to products. Weak acids include carboxylic acids, and we're going to take 3 visual looks at the same exact reaction. So for example, here we have acetic acid, CH3COOH. It's what gives vinegar, again, its punchy taste. We can react it with water, and we use an equilibrium. Whoa, whoa, whoa. We use an equilibrium arrow, and we have our products, acetate and hydronium. So we could represent it like this. This is a visual representation of what happens. We could write it like this. This is the written out form. So CH3COOH reacts with H2O and forms CH3COO- and H3O+ hydronium. Or again, with weak acids, we can just kind of ignore what water's doing in there. Water isn't trickling in between. It's allowing this process to be facilitated here, but we can treat H plus and H3O plus as the same. So that's a perfectly viable way of writing it. The other type of weak electrolyte that you want to know, amines. Amines are weak bases. So there's the example from the previous slide, NH3 reacting with water to form NH4 plus and OH minus. Non-electrolytes. It's kind of a catch-all category. Basically, for our purposes, everything else. So non-electrolytes do not dissociate into ions when dissolved. It includes everything except for strong electrolytes and weak electrolytes. Okay, and we'll do a little summary of that in just a moment. So for Chem 110 purposes, essentially most covalently bonded compounds, except for acids and bases, okay? So some examples, sugars. Here we have a monosaccharide and a disaccharide. Some functional groups that are non-electrolytes, alcohols, ketones, esters, etc. So a summary of these, the strong electrolytes are our ionic compounds, our strong acids, and our strong bases. Our weak electrolytes are carboxylic acids and amines, and our non-electrolytes are basically everything else. That's a generalization, but it's one that works well for our purposes. So thank you all for your time. Hope that you have a spectacular rest of your day, and catch you soon.